Hi everyone, welcome back. Today my topic for this video is the introduction to language model. I'm going to discuss language modeling task in detail in this particular video and the techniques before the generative AIs or before the transformer era. So here basically I'm going to discuss the NLP techniques like the statistical model for the language task and the machine learning model and deep learning neural network like the RNN, LSTM. Those things I'm going to discuss in this particular video. And again, this video also the prerequisite for generative AI. So this is my second video regarding the prerequisite. In previous video, I cover the NLP in details, like NLP steps or NLP project workflow in detail. And this is the second video. So if we talk about the language modeling, so language modeling is a task on which we basically predict a word in a sentence or multiple word in a sentence. For example, if we feed this data like the boy went to, and then our problem is to predict next word after the. So our problem here, we can predict a word as per the probability. As per the probability, we can predict a word after this the. So there is that as shown in this image. You can see here in this image. This is the sentence. The boy went to the, and we have the two option in this image: park and grocery. Either boy went to the park or boy went to the grocery, but our model predict based upon the probability. So you can see here, this is the probability value 0.36, 0.15. So based upon these probability score, our model basically predict the next word. And further after the park, then this is the next word, and this one the probability. You can see here probability, and again here. So this way, basically, this is the high level idea, like how the language model work, how the language modeling work in NLP. And let me discuss this in detail. So language modeling is a task. You can see here, language modeling is a fundamental task in NLP, natural language processing, that involves predicting the next word in a sequence, as I discussed in the image in previous section, given the previous word. So previous word or previous sentence is already given, then our model predict the next word. The primary goal of the language model is to assign the probability to sequence of word, as we discussed in previous image. And so this is the primary task of language model. So language model can be categorized into different category. For example, basic one is the statistical model. Basic language model, basically the statistical model which we use the in which we use the n-grams. And in case of deep learning, we have the RNN. RN stand for the recurrent neural network. And also the advanced version of RNN is LSTM. LSTM basically the long short-term memory network. And the latest one, advanced one, is the transformer based model. Like currently we have the GPT-4 or GPT-3. Those model basically the transformer based model. Even in Llama, Mistral, in Gemini, all these model basically the transformer based architect. So this is regarding the category of language model. So first we discuss about the statistical model. The statistical model basically rely only on the frequency of word. It basically calculates the probability by the frequency of word occurrence in a particular corpus. So based upon the frequency of word in a corpus, it basically calculates the probability and then predict the next word in a sequence. And the neural language model, basically the deep learning based models, those basically the neural network based models. And example of deep learning neural network in language tasks, basically RNN and LSTM. So let me discuss in detail. So before jumping to the statistic model or the neural language model, first we are going to discuss the importance of language model in NLP. Why this language model is so important? Because this language model is play a very crucial role in NLP task, in many application of NLP. For example, if you are working on understanding of context or meaning of some textual data, some language, So these language model basically help us to understand the context or meaning of the sentence, meaning of the document, context of the document, or summary of the context of the summary or context of the chat. So this way, basically, these language model help us to build the AI solution or generative AI solution or deep learning based solutions by understanding the context and meaning. And by predicting the probability of word or sequence of word, language model can interpret more accurately. So as we know, like these language model basically work on the probability by predicting the probability, so they can understand the text context better. And further, we can use the same model for the sentiment analysis and question answering for variety of tasks, basically, where we can use the understanding of context and meaning. So next task is the text generation, and these one of the most visible application of the language model is text generation. And from simple statistic model or simple autocomplete NLP functions to language model can generate the human like similar to the human text. And this applications we use these capability, basically text generation capability we use for the chatbot, for the autocorrect, autocomplete, and for summarization as well, for the story creation. And currently we are using the GPT, like the GPT type models like GPT-4, GPT 3.5, or Gemini or Llama models for these tasks. And one of the advantage of these language model is to improve the machine translation as well. And we can use this to the translate one language to another language. And also we can use these language model for the speech recognition and conversational AI. If we have the any problem in hand related to the speech recognition, we if we work on the speech recognition domain, then we can use the language model to recognize the speech and then convert into the text by predicting the next word in the sequence. So in case of RAG system like the information retrieval or search engine, we can use the language model. These language model basically help our system to retrieve the most relevant information. And for the text summarizations, next advantage of language model is the transfer learning. We can use pre-trained language model for the different tasks, and we can fine tune our pre-trained model for a specific task. And it also helps us to reduce the bias and improve the fairness, and also support the accessibility. And further, these are the common advantage of language model. So let me move to the historical evaluation of language model, like from n-gram, from statistical model to the transformer based architect. So if we talk about the historically, so n-gram basically founded in 1940. So you can see here, like this concept n-gram statistical model concept is too old. It's almost 80 years, or you can say the more than 80-year old. And the concept behind the n-gram model is basically it used the statistical model to predict the next word in the sequence, as we discussed in earlier also. Like we given the previous words n minus words to predict next n word. And the n-gram, basically if we use the n value is 2, then we can use the bigrams. If we use the n value is 3, then we can use the trigram or 4 gram 5 gram as per the value of n. And if we talk about the advantages, and further I will discuss these n-gram in detail as well in lower section with code. And here basically I'm discussing about the historical evaluation of language model, so that's why I'm discussing in short. And in case of advantage is simple, data driven, so it basically straightforward, and it work on the frequency of words, so that's why it's simple and data driven approach. And in case of limitation, definitely there has a certain limitation, context limitation. It didn't capture the long range dependencies, and also the data sparsity problem. And applications, we use application for the like the spell checking, text prediction, speech recognition. In these applications we basically use the n-grams. Currently we have the large language models, but earlier we use these n-gram models. and after the n-gram model, then deep learning come into the pictures after the statistical model. And these neural network basically founded in 1990. And the neural network model, basically the neural network architect, where we use these neural language model architect to predict the next word. And we call this is a simple feed forward neural network. And so this is here like the this kind of architect. Let me explain with the help of some drawing. So these are the basically our activation function, and here basically our input. This is our input. Input means our word here, because we are working on the language task. And these are fully connected layer, as we discussing about the simple feed forward network. So this one, the one of the example of feed forward network, simple feed forward neural network. And here, as we mentioned, like earlier in the earlier of 1990s, or you can say the 2000s, generally we use the simple feed forward neural network for this language task also, like to predict the next word in the sequence. But this is not the right approach or right model for the language specific task, because in the language we have the sentences, like for example, this is the sentence, these are the multiple words. Or you can say this, we can take the example of this particular sentence, like LSTM are capable of learning the dependencies over long range. And suppose we remove these three words, and if we want to predict these words with the help of language model, so these models, like these statistical model or these feed forward neural network model, is not able to predict the next word correctly, because they are not able to capture these dependencies, like the previous word dependencies, long range dependencies, or the long range context. So to overcome this challenge, the RNN come into the picture. So first RNN architect is introduced in 1980, but it popularized after the feed forward neural network after the 2000, or in the 2000 it basically used in industry to handle the sequential data, as I discussed here. And it basically capture the previous words data or sequence data to capture the long range dependencies. But RNN specifically designed to capture the long range dependencies. And advantage over the statistical model or the feed forward neural network, it understand the context by using the previous word data, or by using the previous multiple word data, like the long range dependencies. And further, it has some limitation as well. Vanishing gradient basically a problem while we trained our neural network or our RNN model. It basically unable to update the gradient, or you can see here, like the gradient become very small, so that update the weight. In training, we know in the training of any AI model, we update the weight of the layer. And if our gradient is vanish, then the gradient value is too small, and then we stuck in some of the local minima or spot where we didn't find the optimal solution. So this is the one of the limitation, vanish gradient. And so in this particular video, I'm not going to detail regarding the vanish gradient problem, because as I mentioned earlier, because this video is related to prerequisite. I'm not focusing on much on RNN, LSTM or vanishing gradient. My focus only on the generative AI, and this is second prerequisite video, so that I will give you the clear picture, like before the generative AI, what kind of techniques, what kind of model we have. And the next advanced variant of RNN is the LSTM. LSTM basically the long short-term memory network, and LSTM introduced in 1970, and it basically designed to overcome this vanish gradient problem of RNN. And here in LSTM, basically yeah, we use the different gate. Here are the gate mechanism. One is the input gate, forget gate. Those basically we use the three gates in LSTM. I will discuss in detail as well in next section. And advantage, it basically effectively capture the long range dependency. and it use before the transformer, it widely used for the machine translation, speech recognition, text generation task. So this is the one of the advanced model in deep learning before the transformer era. And then attention come into the picture. So attention basically allow us to focus on specific part of input in a sequence or specific word in a sequence without take care of the sequential data as in LSTM or RNN. We focus in the sequential one by one sequence, and then we retain the information with the help of hidden state. Those things I will discuss in later section. But in the attention mechanism and attention introduced in 2014, it allow us to focus on a specific word. It provide the weight to a particular word based upon their relevancy or based upon the importance of word, and it consider the context of the neighbor word as well while performing the attention. And it widely used for the machine translation and summarization multiple tasks. And this is the core of the transformer. This is the core of the transformer, attention. And I will discuss in detail from mathematics to code part of this attention mechanism in our one of the video related to the transformer architect. But here I'm just giving you the idea regarding the historical evolution of language model. And then in 2017 transformer model introduced, and those model basically introduced by Vaswani in one of the research paper. Attention is all you need, and this is the like the this is the starting of the new era of language model. This is the new type of model, and this transformer model basically, these transformer model don't rely on the sequential processing like RNN, LSTM, or the language or the statistical language model. Those rely on the sequential processing. But transformer model do not rely on the sequential processing. Instead of sequential processing, it use the self-attention mechanism to process all the word in a sequence in parallelly. So architect of transformer model, it has the encoder, decoder, self-attention, feed-forward network, and I will discuss these things in detail as well as I mentioned in the transformer architect video. So this is the architect. In the architect, we have the encoder, decoder, and the self-attention feed-forward network. And advantage, yeah, this is the one of the most advanced architect. It support the parallel processing, scalability, bidirectional. So these are the main advantage, and currently most of the model using the transformer architect. And if we talk about the applications, yeah, in BERT we have the transformer architect. In GPT we have the transformer architect, and latest GPT-4 also transformer based architect. You can say in almost in every language model basically transformer based architect. Behind the every transformer every language model we have the transformer. Yeah, we can say this in behind the every language model. Now I'm going to discuss statistical model or the RNN and LSTM in detail. So first I'm going to start with the statistical model or n-gram model, like how the n-gram model work. So as I mentioned earlier as well, so n-gram model basically rely on the probability of word, and probability of word basically calculated by using the frequency of particular word in the corpus. So this way basically we use the probability of particular word to generate the word in a sequence. And here are the details. So statistical language model are the fundamental techniques in natural language processing, predict the probability of sequence of word. So basically it predict the probability of a sequence of a word, and it model use basically n-gram, and here n value define. If we have the n is 2, then we use the bigram. If n is 3, then we use the trigram. If n is 4, then we use the 4 gram, 5 gram. And here are the mathematics, or here are the calculation details. So regarding this n-gram model, for example, if we go with unigram, n is 1, then we go with unigram. If n is 2, then we go with bigram. In case of 3 is trigram, 4 is 4 gram, 5 gram. And suppose this is our sentence: the quick brown fox jump. and we use the bigram, then we can divide these sentence into this way in bigram. These are the bigram, basically pair of two words. And the advantage, yeah, we discussed earlier as well. Advantage like these are the simple model, very basic model, and efficient and data driven, because these depend upon the frequency of word, and so these are the data driven. But they have the certain limitation, like the context limitation. They didn't understand, it didn't capture the long range dependencies, data sparsity, or lack of generalization. And here are the mathematics regarding the n-gram model. So if you are working on the unigrams, for example n value is 1, then we basically calculate the product of probability of single word. And here are the probability, you can see here probability of first word, probability of second word, up to the probability of n word. Then we perform the multiplication of this probability, and by using this multiplication we can calculate the probability of particular sentence this way. For example, this is the sentence, then we calculate the probability of each word in case of unigram. In case of bigram, then we consider the probability of dependent word, like the next word is depend on the previous word. So here are the like probability in this way, like this is the first word, then the second word is in second word we use the conditional probability, like the first word is given. Here are the probability of second word given first word. Here are the probability of third word given the second word. This way basically we calculate the probability in case of bigram model, then in case of trigram model. And here are the code part. You can see here are the code part, and counter basically we are using to calculate the number of word, and default we are using the dictionary. So in this code, the first method we are using to build our bigram model, second method to calculate the probability. And if we talk about the code part, first we are performing the tokenization here by splitting our corpus. Corpus means our text data, string data into the word by splitting method. This is the simple string splitting. And then we are using the here counter, and in the counter basically we are developing our dictionary here to store the bigram with count. You can see here default for the dictionary, to create the dictionary with count. And here basically we are count the occurrence of each bigram, and here we are calculating the probability. So this way basically we are developing our a simple bigram model, and definitely we have the certain library for this bigram models or the statistical model, but to explain in detail, that's why I write the code here. And this is the corpus we use to develop our bigram model, and this is the sentence for which we are predicting the probability. And next one is the RNN. RNN basically the deep learning based neural network, and in this RNN basically we capture the long range dependencies. And if we talk about the structure of the RNN or architect of the RNN, here you can see that see these are the input X, these are the input in RNN, and T basically stand for the timestamp. Here are the timestamp. And in case of sequence or in case of sentence, this is the third word. You can see T1 is the first word, T2 is the second word, third word, or fourth word. And this H basically the state from the previous layer or previous word. This is the state of previous section. You can see here this is the state. So here basically RNN work like the RNN has the series of layer, and each layer output is depend not only the current input. Current input is this X is the current input, but it layer output is not only depend upon current input but also the previous layer hidden state. So it consider two things while generating the output: previous layer hidden state, this and this input, current input, and previous layer hidden state. This structure of RNN enable to maintain the memory of sequence and making the effective modeling at the time dependent or sequence dependent data. T1, T2 basically stand for the time, but in case of sentence, these are the first word, second word, third word. And the key component in RNN is the recurrent cell, which process one element in the sequence at a time and maintaining the hidden state, as I explained here. So these are the main things or main architect of the RNN, and let me explain the mathematical representation or mathematical formula of RNN. So as I explained, xt we represent the input. These are the input. Ht basically the hidden state. These are the hidden state. And Wt and Wx, these are the weights with respect to hidden state and with respect to input. Wx basically the weight with respect to input, and Wh basically the weight with respect to hidden state, and BH basically the bias. Here are the things to calculate the hidden state, to move hidden state to next level. This is the formula to update the hidden state. Like we are using the 10h here. 10h 10h basically the activation function, and we are passing the hidden state of the previous section, and then we are using the weight. We are multiplying weight with previous layer or previous state, and then we are adding the quantity of current input into current weight. We have the weight and dot product with current input plus bias. So this is the formula to calculate the hidden state, and this is the formula to calculate the output. In the output we are passing the hidden state. You can see here are the hidden state, and weight, these are the weight with respect to output layer, and these are the biases, and under the hidden state we have the input. So you can see here, recurrent neural network rely on two things. One is the hidden state, second one is the input. Not only the input, here are the two things. And if we talk about the Python, generally in Python, basically we use the PyTorch or TensorFlow or Keras to implement the RNN. Simply we need to import the Keras, or we need to develop the layers as per the RNN architect or as per the LSTM architect. But here I intensely use the Python, simple Python without the Keras or TensorFlow. So here I'm using the NumPy here. Here I'm defining a sigmoid function, a 10h function, and here I'm defining the dimensions. These are the input dimension, hidden layer dimension, and output dimension. Here I'm initializing the weight, and here I'm using the NumPy to generate the random weight. You can see here random weight, and here the zero weight for the bias, and here again the previous hidden state weight, and here I'm defining the input sequence, and then I'm defining the forward pass here for the RNN. And then we have the back propagation. So forward pass and back propagation, basically the concept of the training of neural network. So let me explain with the help of this drawing what is forward pass and what is back propagation. So suppose we feed the input during the training of our data. So this is the training data we are feeding to our neural network, and this data going to layer, like input layer to hidden layer, this way, and then the output layer. So training data goes from here to input layer, then the hidden layer in this activation function. This moving data from here to here up to the output layer. So based upon these training data, activation function, and weights, our output is generated. So our output generated here, this whole process is called the forward pass. And based upon this output in the training phase, we calculate the loss here with the help of one of the loss function as per the project requirement, as per the data, or as per the problem in hand. We calculate the loss here, and by using these loss we update these weight through back propagate. Let me change the color. Then we update weight on every layer and move in back direction, updating the weight with the help of gradient. And if we want to discuss the mathematics regarding the gradient update, it will take time definitely. So here just I'm giving you one of the idea, like we are updating this weight by calculating the partial derivative with respect to loss, and moving to this back direction. We call this is the back propagation. Back propagation means we calculate the loss. Based upon the loss we calculate our gradient and then update these weight in each layer. And here basically to update this weight we are using the partial derivative, and then we use the chain rule here chain rule from the mathematics. So this whole process is called the back propagation. And in RNN, we have the time, we consider the sequence of time. So it basically called the back propagation throughout the time, BPTT. And here are the steps for back propagation. First one is the unrolling of RNN and forward pass, as I explained, and then backward pass, and then the weight updation. We update the weight and biases. So these are the training mechanism of the RNN. So this is the code related to the RNN, and this code I explained earlier. This code basically cover up to the forward pass, and here basically we are initializing our gradient. As I explained, these are the derivatives. So, and here basically I'm updating the gradient value during the backward pass. So this is the back propagation throughout the time code in Python. And intensely I developed this code in Python, but in real time in project we use the PyTorch, Keras or TensorFlow as per the requirement. And further regarding the application, we have the certain application on which we use the RNN, like the text generation, speech recognition, machine translation, sentiment analysis. And regarding the limitation, definitely vanishing gradient, we already discuss these things. And training instability, because recurrent nature, we have the certain problem of vanishing gradient or exploding gradient. So these are the one of the limitation. Memory also, to capture long range, like if we have the long corpus, then it had the memory limitation also. And to overcome the RNN problem, then the LSTM come into the picture. LSTM basically stand for long short-term memory network, and this is specifically designed to overcome the RNN problems. In RNN, we see few problem. One is the vanishing gradient. Second one is the challenge while retaining the long-term dependencies in sequential data. So LSTM basically designed in this way to solve the RNN problem. And here are the high-level overview of the LSTM. And in LSTM, we have the three major part. Core of the LSTM has three major part, three gates. One is the input gate. This section is the first one is the forget gate. Like one is the forget gate. This section basically the forget gate. Then we have the input gate. This one is basically the input gate section. And then we have the output gate. So these are the major part of the LSTM, and I will explain the mathematics and core idea of the LSTM as well with the help of this image. And further I have some equation as well here. So the input here, xt is the input at current time. So x is basically the input. ht minus 1, this one is the previous hidden state. ct minus 1 also the previous cell state. So here is the two things. In RNN we have the only hidden state and input, but here one more thing added is the previous cell state. This is the new. This is specific to LSTM. In RNN we have the hidden state, we have the input, but here are the three things. One is the input, hidden state, and the previous cell state. And then we have the sigmoid function. These are the sigmoid functions. And we have the 10h also. Here are the 10h, and these are the product. These are the product, and this is the summation. And product means here dot product basically. And then this is the current state cell. This is the hidden state of current hidden state. And so this is the high level overview of LSTM. If we feed our input and previous hidden state, then we perform the sigmoid, and then we perform the multiplication product between the previous cell state and the sigmoid or sigmoid value of our input and hidden state, previous hidden state basically. And in the input gate, again we are performing the sigmoid for our previous hidden state and input, and then performing the multiplication between the 10h of, and in the 10h again we are passing our previous hidden state and input, then performing the multiplication after the 10h value. And this is the candidate cell basically, candidate cell state basically, and then performing the summation. So this forget gate, this one is the forget gate. This one is responsible how much information we want to forget from the previous candidate cell or from the previous state, previous cell state. And input basically responsible to add the information from the new input, from our new input and the hidden state. So further we have the output gate. Output gate basically responsible how much information is passing to next cell. So let me explain with the help of mathematics. So these are the three main part or main gate of the LSTM. One is the input gate, and this control how much information, new input of information will be stored in cell state. Forget gate, this decide what part of previous cell to be retained, like what part we need to forget and what part we need to retain. And output gate basically responsible determine how much cell state to the output. So, and we are using the sigmoid most of the time. I think three sigmoid function we have, as I explained in the image as well. So output in case of sigmoid is 0 and 1. 0 means completely ignore, 1 means completely retain. And let me explain you equation part. So as I explained earlier as well, so x basically the input, ht minus 1. Ht minus 1 is basically previous hidden state. Ct minus 1, this one the previous cell state, and the output is the new hidden state is ht, updated cell state is ct. And then we have the gates. So first one is the forget gate. So let me explain the forget gate here. So forget gate determine what information from previous cell state, means ct minus 1 should be retained or discard. This is the responsibility of the forget gate, like how much information from the previous cell state we need to retain, we need to save, or we need to forget, or we need to discard. And how basically forget gate is work, it performing the sigmoid. You can see here wf and bf, these are basically the weight and biases. F means forget gate weight, w and f means forget gate weight, b means bias, f means forget gate bias, and ht basically the previous hidden state, and xt basically the input, and sigmoid basically this is the sigmoid function. So this is the mathematics behind the forget gate. Then we have the input gate. Under the input gate, input gate basically decide how much new information in our input xt should be stored in current cell. So this gate, input gate basically responsible to store the information from the current input in current cell, like the new from the new input in current cell. And again here also we have the sigmoid function, and in the sigmoid function this again the weight regarding the input gate, this bias again for the input gate, this is the previous hidden state, this is our input. And then we have the another things is the candidate cell state. Here we are performing the 10H, and in the 10H again we have the weight and bias and hidden state and input. Then we have the update cell state, and update cell state basically combination of previous cell state minus t minus 1 plus multiply the forget gate output. Forget gate basically ft. So we are multiplying our forget gate with previous cell state plus candidate. Here basically we are performing the summation as explained in the image as well. So summation between the candidate cell plus input gate. So here are the information from the input gate, then the candidate cell. Let me go back to the image. So here basically we are talking about the current cell state, this one ct, and this is basically the summation between our input into candidate cell and plus our forget gate into our previous cell state. So this one basically we are talking about this part. And let me again back to the mathematic. So this one is regarding the update cell state. Then we have the output. In the output we have the first in output we have the sigmoid as in explained in the image as well. First we are performing the sigmoid, and again this one is the weight, this one is the bias, this one is the hidden state, this one is the input. Then we are performing the 10H. 10H 10H for the current state. Like this current state is the updated, basically updated cell state coming from here. We are performing 10H for this, plus multiplying. You can see here we are performing the dot product between basically output gate information, OT basically the output gate information result. You can say the result from the output gate into 10H of updated cell state. So this way basically the our LSTM is work. And here are the all information if you want to go into the details of these equations. So this is the forget gate equation, I already explained. This is the sigmoid, and this is the weight, this is the bias, this is the hidden state, this is the input, and this is the sigmoid function for the input gate. This is for the candidate cell. This is the 10H function. This is the cell state update, as I explained earlier as well. This is the output state, and this is the hidden state. So this is the core idea and mathematics behind the LSTM. And if we talk about the advantage, yeah, we already know like the LSTM basically designed to mitigate the vanishing gradient problem, so that we can have better trained our model in better way as compared to the RNN architect. And it also learning the long term dependencies. So here are the some implementation for some dummy data set. Like this is the toy data set I created for by using the NumPy, and here I'm using the TensorFlow and Keras. So as I explained earlier as well, so real time generally we use the TensorFlow, PyTorch or Keras. We have the three options. Here basically we are using the TensorFlow and Keras, and in this one basically to generate our dummy data, synthetical data. And then we are defining our LSTM model. LSTM basically sequential model. Then we are adding the layer, and then we are compiling our model, and then here we are basically training our model. So this is the Python regarding the LSTM model, and one of the small model for this learning purpose. And if you execute this way basically it run, and we define the 200 epochs, so it run for the 200 epochs, and after that it basically predict some output we feed here. So this is the high level overview regarding the LSTM model. And further, the advantage or the use case of the LSTM is the we can use LSTM in multiple NLP tasks like the machine translation, text generation, sentiment analysis, time series forecasting, also in speech recognition also. So that's all regarding this video. So in this particular video I cover the introduction to language model. I didn't cover transformer or generative AI or GAN network here, because those I would cover in my next video related to generative AI and transformer. But here basically my focus only on the historical evolution of language model from the statistical or from the machine learning N-gram to transformer, like the transformer model. So here basically I cover the N-gram neural network. In the neural network I basically cover the RNN LSTM. So that's only the topics which I cover. In next video I go for the advanced part like the GAN part, transformers, and then the advanced variant of transformer as well. And thank you.